Okay, I'm starting here because I'm not really sure exactly where the video cut off last, but our electrical impulse started in the SA node, went down through our AV node, the bundle of his, split into the right and left bundle branches, and now we're moving on. Our electrical impulse is going to our Purkinje fibers, which string along here and here. Oops. Yes. Did I talk about, I don't think I got this part. Oops, I'm confused where I'm at here. Okay. Anyway, so in conclusion, sorry about that. The SA node initiates the electrical impulse. It travels through the atria, through the AV node, delays the impulse momentarily so that the atria can release the blood to the ventricle. The AV node conducts the impulse down to the bundle of his, through the right and left bundle branches, ultimately to the right and left portions of the heart through the Purkinje fibers. Okay? If the electrical current is not coordinated, the pumping action of the heart will not be effective, obviously. So if you've got one part firing and then another part firing, instead of it firing in unison, it's not going to pump the blood out of the heart correctly. So again, the backup system, the SA node initiates it. If the SA node fails, the AV node picks it up. And the AV node is the one coordinating the contraction. Your heart rate will be at 60 or less. Okay? From the AV node, and then if the AV node fails, then the underlying ventricular tissues, it moves on to the bundle of his, and your heart rate will be at 40 or less. Okay? So again, the SA node, AV node, all that stuff is also what's shown on your EKG. So the actual cardiac conduction cycle is what we're moving on to now. Okay, scratch what I just talked about. We're moving on to waveforms. So, if you're looking at this is a waveform. This is what a normal EKG should look like. Let me blow this up for you. This is what a normal EKG should look like. Okay? So, the esoteric line is just the baseline. Okay? So right here, you can see right here, the baseline. The esoteric line is right there. Okay? And if things go above or below it, it represents the absence of electrical activity. This is where the beginning of the waveforms are marked, and the ending also. So, as you're looking at this, like I said, this is a normal waveform on an EKG. So you will have a P wave, which is right here, a Q wave, an R, S, T. Okay? The P wave is when the SA node initiates, causing depolarization of the atria. So if you remember, think back, what was depolarization? Look at your little circles. Okay. P wave represents the depolarization of the atria. Okay. And that is the very first wave. Okay. The QRS complex. So it's QRS complex is what that's called. And that is electrical impulse that travels, when the AV node is delayed slightly. Okay. Onto the bundle branches, the right and left bundle branches. And then ventricular depolarization occurs. Okay. QRS complex. Ventricular depolarization. Key there. Okay. T wave. T wave is the resting state, the repolarization, when the ventricles, relax. Okay. Each EKG reading should have a clearly defined PQRS wave form. If they do not, that means there is an abnormality somewhere. Okay, and we're going to discuss all that later, what the abnormalities are and what abnormal and semi-normal PQRS waves look like. Okay, I just wanted to show you this little gem too, because this might help put this in perspective for you. So again, here's our SA node, AV node here, bundle of his, right in the bundle branches, Purkinje fibers. So distally, no electrical activity happening here. Atrial depolarization when the SA node is firing. Again, that initiates our P wave. Okay. When the AV node is holding on, that shows our PR interval, which we haven't talked about that very much just yet. Ventricular depolarization, again here, that's the beginning of the QRS. Ventricular depolarization completely is when you have your QRS complex, and then ventricular repolarization, everything is calming back down. That's your ST segment, your T wave. Okay, and this is another great representation here of the cycle of events that happens here. So we've got our start, we've got the P wave atrial depolarization, we've got our atria is contracting, we've got our P wave now, the atria, the AV node sends it on, so we've got the beginning of our Q wave. It keeps on going through the Purkinje fiber, or bundle of his, that starts to make our Q, spiking our R. Through the Purkinje fibers, we have the R to the S, and then our S, ventricular contraction has occurred, and then our T begins our repolarization. At the end of repolarization, we have our full T wave. So again, P wave is atrial depolarization. The QRS is ventricular depolarization, and then our T represents ventricular repolarization. Okay. All right, so we're moving on to the part where we figured out what our normal PQRS wave is supposed to look like, but how do we know if people's are normal? Okay, if you can get your textbook out on page 1081, figure B shows the EKG paper and what it looks like. This is just another representation of that. So it's nothing but a bunch of tiny squares inside of a bigger square. Okay? And if you're looking on page 1081, you'll see some lines up at the top that go up there, and it has the 3 seconds. Okay? So each one of those sections equals 3 seconds. Okay? And then this one big square right here. Okay. So each square on here represents time. So our time runs lengthways, okay? And then MV, those millivolts I told you about, runs up and down. So we measure millivolts going this direction, up and down, and we measure time going in this direction right here, okay? So this one big square right here equates to 0.2 seconds. Okay? 0.2 seconds. Alright? So, this is 0.2 seconds, 0.2 seconds, 0.2 seconds, 0.2 seconds, 0.2 seconds, 0.2 seconds. Okay? The big square. Okay? The little bitty tiny square inside here is where they pulled this picture out. This little bitty tiny square equates to 0.04 seconds. 0.04 seconds. Okay. It also equates to in our height-wise 0.1 millivolt. Okay? 0.1 millivolts. So if we add all of them together, going lengthways, the bigger square, the big red square, lengthways is 0.5 millivolts. Okay, guys, I hope that makes sense to you. So again, we're talking time going on the horizon in seconds. The big square is 0.2 seconds. Okay, the little tiny square equates to 0.04 seconds. Okay, time-wise. Now, height-wise, the big square is 0.5 millivolts, and the teeny tiny square from here to here equates to 0.1 millivolt. Alright? So we use all of these numbers to calculate our waveforms, and that is what we're going to start on next. Alright, so when I'm going to analyze an EKG, the first thing that I start with is the rhythm, or the heart rate as it's called. Okay? And remember when I told you just a minute ago that you would see those little hash lines? There they are. So from here to here equates 3 seconds, and from here to here equates 3 seconds. So to calculate a heart rate, we need a 6-second total. So we have to count from here to here to get our heart rate. Okay? This is called the 6-second count method. Okay? The 6-second method. It's very, very simple. Is all you have to do is count the number of R complexes, the R waves, and multiply it by 10. So, as such, we go 1, 2, 3, 4, 5, 6, 7. 7 times 10 is 70. So thus the heart rate, or the rhythm of this EKG, would be 70 beats per minute. Okay? So R wave, R wave, R wave, R wave. That's the simplest way to calculate the heart rate on an EKG. 6-second method. Okay, so would this rhythm be normal or abnormal? Well, to know that question, or to answer that question rather, you would have to know what the normal heart rate is. And what is our normal heart rate? 60 to 100 at resting. So is this patient's heart rate within normal range? Yes, because it's 70. Okay? So that's the first thing you do whenever you're going to analyze an EKG to figure out whether it's normal or abnormal. When we start, move on to lecture number 3, and we're going to dive into looking at the P wave, the Q wave, the QRS complex, and the T wave to distinguish whether we have abnormalities or not.